Hi everyone, this is Kalyan Kumar and welcome to Chemistry Tutorials. We've been doing a series of lectures on atomic structure, and in the last episode, part 4, we talked about the Geiger-Marsden experiment and how the results of this experiment led to the Rutherford's model of an atom. How Rutherford bombarded alpha particles on a thin gold foil and based on the results of it concluded that the atom has a central core called the nucleus where the entire positive charge and mass of the atom is concentrated. This video is part 5 of 13 and today we're going to discuss the nature of radiation. So let's get the show on the road. Ordinary light, and we're actually talking about nature of radiations now. Ordinary light, X-rays, gamma rays, etc. are all called electromagnetic radiations and they have wave characteristics. These radiations are called electromagnetic because when they pass through a point in space, they produce oscillating electric and magnetic fields at that point. So when a light is traveling through a particular path, at every point in their path, there is an oscillating electric and magnetic field perpendicular to each other. This was proposed in 1873 by a Scottish scientist named James Clerk Maxwell, who showed that electromagnetic radiations are the oscillating energy densities of electric and magnetic fields. He was also one of those, including Young, who showed that electromagnetic radiations exhibit wave characteristics. In fact, what basically he tries to say here is that whenever there is an oscillating energy density of electric and magnetic fields, an electromagnetic radiation is produced, is generated. Now, among the three most important physicists considered as the greatest physicists of all time, we have Sir Isaac Newton, we have Albert Einstein, and we have James Clerk Maxwell. His findings were so revolutionary, so important, that it completely changed the scenario of optics. Now, Maxwell showed that a static charge or a charge with uniform velocity sets up an electric and magnetic field which gives rise to an energy density in space which is constant. So basically what we're trying to say is that if there is a charge which is static, not moving, or perhaps moving with a uniform velocity, it is associated with an electric and magnetic field which gives rise to an energy density in space which is constant. Nothing happens here. But if the velocity of the charge is changed somehow, the energy density associated with the electric and magnetic field starts changing or fluctuating or oscillating, giving rise to an electromagnetic radiation. So electromagnetic radiation is basically generated whenever there is a charge whose velocity is changing. It may change constantly, it may change inconsistently, but the fact of the matter is if the velocity changes at any given point of time, electromagnetic radiation will be produced. Now, he also revolutionized along with Young to propose that light, rather than traveling in a straight line, is of course traveling in a straight line but has a wave nature. Light is a transverse wave as opposed to sound, which is a longitudinal wave. Remember, sound is not an electromagnetic wave, it's a mechanical wave. Now, there are 4 fundamental properties of any wave, and they are wavelength, time period and frequency, velocity and amplitude. So let's understand each of these, at least the most important ones. Let's talk about wavelength first. Now, what is wavelength? Wavelength is the distance between two successive points on the wave which are in the same phase. Now, what does same phase mean? Same phase implies not only that the displacement of the points from the mean position would be the same, but also that the wave pattern that follows the 2 points will be the same. Now, wavelength is the distance between two successive crests or troughs or any 2 points on the wave that fulfill the condition of being in the same phase. Let's understand this with the help of this diagram. So we can write, since it's a transverse wave, we can show it as a sine wave. Now look at this distance. This is wavelength. Now why do we call this as a wavelength? First of all, these 2 points have the same displacement from the mean position. They are the crests. And as well as that the pattern that follows after this point is downward. Here also it's downward. Therefore, this point to this point is a wavelength, one single wavelength. Now, it need not be from the top point itself. You can take any 2 points. Now, one might wonder, why are this distance not a wavelength? After all, both have the same distance from the mean position, which is this. The reason is, at this point, after this point, the wave is going up, whereas after this point, the wave is going down. And remember the condition, the wave pattern that follows the 2 points will be the same. That means whatever pattern that follows the point should also be the same. So from this point onwards, if we draw a straight line and we reach here, this is the wavelength. Because from this point and this point, the displacement from the mean position is same, and from after both points, the wave is rising up. Of course, even this could be dubbed as a wavelength. The points where the amplitude is zero, where the displacement is zero rather. Now, wavelength is denoted by lambda and is measured in the units of length, because it's basically a length. Time period, on the other hand, is the time taken by the wave to travel a distance of one complete lambda, one complete wavelength, and it is denoted by t. Frequency is the number of waves contained in 1 second, and it is denoted by nu. Remember, number of waves, one wave traveling one wavelength is one wave. So frequency is the number of waves, where one wave is the amount of wave contained in one wavelength. Contained in 1 second, it is denoted by nu. Now, if in t seconds, you have one wave. If in t seconds you have one wave, I think it's wrongly appearing as number of waves, it should be one wave. In t seconds, because time period is the time when you travel one complete wave, one complete wavelength. So in t seconds you have one wave. So in 1 second, how many waves will you have? It is automatically going to be 1 by t waves. And that is what is frequency. Velocity of a wave is the distance it travels per unit time. It is denoted by c. Since it travels a distance lambda in time t, the velocity obviously will be distance by time taken, lambda over t, or lambda nu, or lambda f. Sometimes frequency is denoted by f instead of nu. And it has been found out and calculated that the velocity of all electromagnetic waves are the same. In vacuum, their velocity is 3 into 10 to the power 8 meter per second. They only differ in their wavelength and frequency. So red light, blue light, yellow light, they all travel with the same speed. The only reason they look different, they appear different, and their behavior is different is because of their different wavelength and frequency. Obviously, wavelength and frequency have to be different so that the product of these two remains constant. So that is the end of nature of radiation. This is what we're going to do in video number 5 of 13. In the next part, we are going to be doing atomic spectra, where we talk about the different types of radiation that atoms emit, emission spectra, absorption spectra, and things like that. So I hope you were able to understand the nature of radiation by this video. If you have any questions, queries, any suggestions, any comments, any doubt that you have, please drop them in the comment section below. If you haven't subscribed to this channel, please do so at the earliest, because I'm going to be posting lots and lots of chemistry videos on different lessons. I'll be doing a lot of lessons in physical, organic and inorganic chemistry. So it's very important for you to subscribe, because if you subscribe, you get the notification that I've posted a video the moment I do so. If you like this video, please do hit the like button too. This is Kalyan Kumar signing off. Have a great day and thank you for watching.